Hi, this is about the optimal binary search tree. Okay, before I go to optimal binary search tree, first let us understand what is a binary search tree. So, what is a binary search tree? If there is a root, okay, its left child will have lesser value than the root, and its right child will have the greater value than the root. Okay, that is how it works. See this example over here. Okay, this figure A. The root is 10, its left child is 5, and its right child is 25. You see that the left child is having lesser value than the root 10, and its right child, that is 25, is having greater value than 10. Okay, that is binary search tree. Now we have the next topic called as optimal binary search tree. See the definition. Okay, it is also called as a weighted binary search tree. Okay, it minimizes the expected search cost. Okay, it minimizes the expected search cost. See, for example, okay, if I look at this tree itself, if I look at this tree A, okay, I'm trying really hard to write here. Okay, see, if I want to find the element 10, okay, so I always start, if I want to search an element, I will always start from the root. So I will start at the root is 10. Okay, and I want to find 10 itself. So how many comparisons I need to do? So immediately in the first search itself I am getting the value. So I need only one comparison in order to find the value 10. But if I want to find the value 5, if I want to find the value 5, first I have to go to the root 10, so one comparison. From there I will come to 5. So two comparisons are needed. Likewise, here if I want to compare 20, see, if I want to compare 20, first I will start at root 10, so one comparison. Then I will go to 25, that is second comparison. Then I will reach 20. So three comparisons are needed, correct? So here also if you look at figure B, okay, if I want to find the element 15, if I want to find the element 15, I will start at root 10. So one comparison. So then from 10 I will go to 20. So two comparisons. From there I will come to 15. So when I reach 15, I have found the element. So total number of comparisons needed are 3. So a binary search tree with some cost. Here the cost is the number of comparisons. So this can be considered as an optimal binary search tree. But the problem here is, okay, out of many binary search tree, here also if you see the nodes are the same. See 5, 10, 15, 20 and 25. In tree B also the nodes are having the same values 5, 10, 15, 20 and 25. So if they are having same values, which do you think is the most optimal or the one which is having the least cost? Okay, so you need to have least cost. So how do you find that? See here in the next part, when there is ideal condition, we have given how do you find the cost. See here, okay, in the tree A, one minute, in the tree A, the highest number of comparison is 4, whereas in figure B, that is tree B, the highest number of comparison is 3. Okay, so which do you think is easy? I mean, which one is much better? So because the number of comparisons in tree A is more than the tree B, so we can say that the tree with very less number of comparisons, that can be considered as the most ideal binary search tree. But okay, so one more thing is there. Now, if I want to find element 5 in this tree B, for example, if I want to find the element 5, okay, so I will start at 10, then I will reach 5. So I need two comparisons, correct? So if I want to find the probability, how do I find the probability of finding a given node? See, what happens is, I know that there are two comparisons that needs to be done. But what is the probability? You know that if there are, if there is a dice game, okay, that Ludo game. So if I want to get 6, okay, what is the probability there? So dice or Ludo dice is having 6 faces. So the number of probability is 6 times 6, something like 36. Correct. So here what we do is, okay, see how I have done this. Okay, look at this one here. Okay, so the probability, let's say the probability is equal. So total number of probability is 100. How many total number of nodes are there? 5. So what is the probability? It is 20. So we always have the value in the form of 1. Okay, we want the value in the form of 1. So 20 is converted into 0.20. Okay, so when there is equal probability, when there is equal chances of getting a given node, then whatever total nodes you have, okay, that you have to divide by 100. For example, if there is a tree with 6 nodes, what is the probability of that? So it would be 100 divided by 6. So whatever value you get, that will be the probability of the one node, the other node and the other node. Like that it will be. So here you see what I have done. Okay. So it is saying for the first tree the probability is 2.4. But how did I get? See, if you remember in this one, let me erase everything first. Let me write. See here, 10 is having, it needs one comparison, 5, this one needs two comparison, it needs 3 and 4. Remember this, okay. So how do I do? Here you see. So first node is having one comparison. What is the probability? 0.20. Likewise for 2, 2 is, I'm talking about 5. So 5 is having the comparison 2. The probability is 0.20. Likewise, we have done for all of them. So as you can see, it is 1 into 0.20, 2 into 0.20, like that it is going on. Okay, so I'm getting the value is 2.4. Likewise, if I do for this one, let me do for tree B. Let me write this formula, okay, for tree B, this one. See, I am going to write somewhere over here. I can't write it over here, so let me write it over here. Remember, 10 is having the comparison as 1. Okay, here the comparison is 1. So it is 1 times 0.20 plus, come here, this is 5. 5 is having the number of comparison as 2. So it is 2.2, 0.2 into 2 plus, will do for this one 20. The number of comparison is 2. So 2 into 2, 0.20 plus 15. 15 is having 3 comparisons. So it is 3 into 0.20 plus the next one is also 25, also 3 comparisons. So it is like this. So the result I am getting is around, I have done it over here. So the result I am getting is 2.4. 2.4 no, 2.2. Okay. Now, see, this is when the equal probabilities are there. That means I can get the chances of getting 5 is 20%. Okay, so equal probability. But sometimes what happens is we might not have equal probability. Some elements might have no higher chance of getting it. So what we do is, okay, instead of having equal probability, the system, I mean the problem itself gives you the probability. See here. So I think I have a question over here. See, find the expected cost. Okay, find the expected cost. Okay, for the following trees. So what they have done, see here, the trees are having these are the nodes. So the nodes are also there. They have given the keys and they have given the probabilities also. See, it is not 0.2 now, it is 0.3, 0.3, 0.5, 0. Not 0.5, 0.05, 0.05 and 0.3. Now, how do I calculate the cost for this? Wait, 1 minute. Let it. Am I able to write? No. I think I will have to copy paste this. Just hold on a second. And I'll bring it to the whiteboard. Sorry. Okay, here. 1 minute. Okay. See, these are the trees, and now the probabilities are already given. That is not 0.2. They don't have equal probabilities. They are having different probabilities. So the node 25 is having the probability of 0.3. So now, which one do you think is better? So how do you solve this? You write the comparison. See, if I want to find 10, one is its cost. If I want to find 5, two times of comparison is needed. Two comparisons are needed. If I want to find 20, I will start at root. So one comparison and I will reach 20. So total number of comparison is 2. If I want to reach to 15, then the number of comparisons are 3. Here also the number of comparisons are 3. Let me do for this one. Here if I want to start at 10 and I want to find 10 itself, so the number of comparison is 1. Here the number of comparison is 2. Here the number of comparison is 2. Here it is 3. And here it is 4. Okay, why 4? Because if I want to reach 15, I will have to start at 1. So I will have to start at 10. So 1 comparison, here 2 comparison, here 3 comparison, and here 4. So total number of comparisons are 4. So if I want to find the cost of let's say tree 1, it is the comparison. So for 10 it is 1 and its probability. So for 10 the probability is 0.3. So it is 1 into 0.3 plus. Okay. For 5 it is 2 number of comparison and its probability is 0.3. It will be given in the problem itself. And for 20 the number of comparisons are 2 and its probability is 0.05. Likewise, okay, I think you are able to hear some noise. It's because of the train. Okay, next we have 15. 15 is having the number of comparison 3 and its probability is 0.05. And this one 15, so we are done with so we are left with 25. 25 number of comparison this much and its probability is 0.05. So if you are calculating it, we are getting some value. I have written the value. It is 1.85. So the value would be 1.85. Similarly, you have to write the cost for tree 2. So first node is 10. So its comparison is 1. So 0.3 plus for 5 it is 2 comparisons and its probability is 0.3 plus 25 is the next node. So its comparison is 2 and its 25 its probability is 0.3 plus for 20 it is 3 number of comparisons, its probability is 0.05 plus 15. 15 is having number of comparisons 4 and number of sorry its probability is, so we are getting somewhere around we are getting the value as 2.05. We are getting the value as 2.05. Now if you see, the one with the least cost will be considered as a better tree. Okay, so here we can say that the cost of the tree 1 is 1.85 and the cost of tree 2 is 2.05. So we can see that tree 1 is having, tree 1 is having much, it is better behavior, or it is easier, or it is it will take less time. That's what. Okay, that is what it does. And also remember, okay, See, when we are evaluating this binary tree, right? So some nodes are, they are having unequal numbers. So some nodes might not have their child nodes. So if you look at this one, node 5, node 5, okay, it is not having its any child. So what we have done is we have drawn these empty nodes, null links, correct? Do you remember? These are called as internal links and these are called as external links. So this is also, you know, possible in a binary tree. Okay. So see here, internal path and external path length. Okay. So for internal path, okay. See, sorry, 1 minute. 1 minute. Okay, so you can. These are not actually required. These are all like when you want to find the cost and all. So we can do this. Okay. So I will send you a video in which you can actually find. Okay. So here you see. Some consider the following trees. Let's find the cost. Okay. So if you have equal cost, then see here it is 1. Then here the probability is 2. Here the probability is 2. Like that. So then we divide it by the total number of elements like this. Okay. So I hope you have understood. So this is the main problem in that part. It is to find the expected cost. So we do it like this. Okay. So I will stop here. Thank you.